Design of a quantizer mainly involves 3 steps. First, selection of decision boundaries. Second, selection of reconstruction levels. And third, selection of code words. Two performance measures which are associated with the design of a quantizer are minimization of distortion, that is minimization of mean square quantization error, and minimization of the rate of the quantizer. So far in our study of quantizer, we had assumed fixed number of quantization levels and fixed length coding, and therefore, the selection of code word was not an important issue because the rate of the quantizer was decided by the quantizer alphabet size. But now, if we relax the restriction of fixed length coding and move on to variable length coding, then selection of code words will be an important issue because it will decide the rate of the quantizer, which in turn is lower bounded by the entropy of the output of the quantizer. Now, there are two different approaches for variable length coding. The first approach is to directly incorporate the entropy of the output of the quantizer in the design of quantizer itself, which is a difficult approach, and a simpler approach would be to design the Lloyd-Max quantizer, which considers only the minimization of distortion as a criterion and then entropy code the output of this quantizer. Now, let us study the second approach first. This table depicts the entropies in bits per sample for the quantizers designed based on the criterion of minimization of distortion, that is minimization of mean squared quantization error. So, there are two inputs, one is Gaussian PDF and other is Laplacian PDF. For both this input, we design quantizer based on uniform PDF optimized and non-uniform PDF optimized principles. Now, there are certain observations to be made from these tables. First, we find that for the lower levels, that is low number of quantization levels, the difference in rate is relatively small between the fixed rate and entropy coded cases. But this is not the case for higher levels. For example, for 32 levels, a fixed rate quantizer would require 5 bits per sample. However, the entropy of a 32 level uniform quantizer for the Laplacian case is 3.779 bits per sample, which is more than 1 bit less. Another observation is that difference between the fixed rate and uniform quantizer entropy is generally larger than the difference between the fixed rate and the non-uniform quantizer. This is true for both Gaussian and Laplacian PDF. So, for example, if we take number of levels to be 2, the fixed rate quantizer will require 2 bits per sample, whereas uniform quantizer would require 1.904. So, difference between 2 and 1.904 is more than the difference between 2 and 1.911. This is the case even for the Laplacian PDF. Now, the reason for this is as follows. Non-uniform quantizers have smaller step size in high probability regions and larger steps in low probability regions. Therefore, the net effect is that the probability of input falling into a low probability region and the probability of input falling in a high probability regions are approximately close together. And because of this, the output entropy of the non-uniform quantizer is higher with respect to the uniform quantizer. Another observation is that closer the PDF is to being uniform, the less difference in this rates. Therefore, it is observed that the difference in rate is much less for the quantizer for the Gaussian source than the quantizer for the source having Laplacian PDF. Now, as said earlier that entropy coding the outputs of the Lloyd-Max quantizer is a simpler approach, but it would be more beneficial to incorporate the entropy as a measure of rate instead of alphabet size in the design of the quantizer itself. So, let us do this for a specific case where we want to minimize the distortion given the entropy of the quantizer. Now, the entropy of the quantizer output is given by HQ is equal to minus summation j equal to 1 up to L, where we assume that the number of quantization levels are L P j log P j, where P j is the probability of the input to the quantizer falling in the jth quantization interval. And this probability P j is given by integral of PDF over the interval b j minus 1 up to b j. Now, it is to be noted that the selection of the representation levels, that is y j, do not affect the calculation of the rate of the quantizer, which is lower bounded by the entropy. So, what this implies is that y j can be selected solely to minimize the distortion, that is the mean squared quantization error. However, the selection of the decision boundaries do affect both the rate and the distortion. Earlier in our design of the quantizer, we had assumed that the rate is fixed by the quantizer alphabet size, that is the number of levels, and we also assume fixed rate coding and then obtained reconstruction levels and decision boundaries based on the criterion of minimizing the distortion. Now, we can fix the entropy and try to minimize the distortion, and the problem can be posed as follows. For a given rate, determine the decision boundaries b j that minimize the mean squared quantization error, which is given by this expression, subject to the constraint that the entropy is less than or equal to R. Now, the process of finding this optimum entropy constraint quantizer is quite complex, and the details are provided in this reference. So, detailed derivation for this case for the entropy constraint quantizer is provided here. Now, fortunately, at higher rates we can show that the optimal quantizer is a uniform quantizer, and it is also important to state that these results which are valid for the high rate case are also valid for lower rates. Now, for details one can refer to the following paper by Farvardin and Modestino, which appeared in IEEE Transaction on Information Theory in the year 1984. So, in general, design of entropy constraint quantizer is little more complex. Now, we have also seen that any non-uniform quantizer can be represented by a compressor followed by a uniform quantizer and followed by an expander. Now, it is also possible to design a quantizer wherein we try to minimize the entropy given the constraint of satisfying particular level of distortion. Now, this is a very difficult problem, but it is possible to derive the characteristic of the optimum compressor at high rates, which minimize the entropy for a given distortion. So, let us look at this problem. So, we will consider the design of high rate optimum quantization, which takes into account both the entropy and the distortion. So, we will assume that we want to minimize the entropy for a given distortion. We will also assume that is high rate case, and for this case we want to find out what is the optimum compressor. So, in order to do this, so let us exploit the calculus of variation approach, and let us construct the functional J equal to entropy of the output of the quantizer plus a constant lambda times distortion in the form of mean squared quantization error, and then obtain the compressor characteristic to minimize this functional J. We will use the Bennett integral, which we studied in the last class, to characterize the distortion. Now, the quantizer entropy is given by H q is equal to summation of P j log P j. Now, for high rates we can make a reasonable assumption that the PDF P x is constant over each quantization interval delta j, and if P j denotes the probability of the input of the quantizer falling in the jth quantization interval, it can be written as integral of P x dx over the interval b j minus 1 up to b j, and this is approximately equal to P x y j denotes the reconstruction level for the interval b j minus 1 to b j, and delta j is the quantization interval. So, using this we can rewrite the expression for entropy as follows: H q is equal to minus summation P j log P j equal to 1 to L, and this can be rewritten as log of P y j delta j. This can be rewritten as log of delta j Now, in the earlier class we had seen that a compressor mapping in general has the following characteristic, and if the interval is very small for very high rates, then the derivative at reconstruction level y j can be approximated by this expression, and then C of b j minus C b j minus 1 itself is equal to 2 x max upon L, in which case we get delta j is equal to this expression out here. So, this we had seen in the earlier class. So, we will use this result and substitute in this expression out here to get the following expression. So, in place of delta j, we will substitute 2 x max divided by L, the whole thing divided by derivative evaluated at y j delta j. Now, if we assume the rate to be high enough, in that case the quantization interval delta j will be very small, and in that case we can rewrite this expression where summations are substituted by the integrals, and we get the expression for H q as follows. Now, this integral can be broken up into two parts, and finally, we get the expression as follows. Now, let us make a small substitution as z x is equal to the derivative of C x, and if we do that and rewrite the expression and also write the Bennett integral for distortion in the expression for j, we will get as follows: j is equal to this is h q which we just derived plus lambda times distortion, which can be written based on what we did last time as 3 L squared x max minus x max, where we have substituted z x for derivative of C x. All these integrals are over minus x max to plus x max. Now, to minimize j, we can differentiate j with respect to z and equate the result to 0, and this will give us the following expression. So, this implies that z x is equal to root of 2 lambda by 3 times x max by L, which itself is a constant. Let us call it as gamma, and therefore, C dash x is equal to gamma, which implies C x is equal to gamma x plus beta, where beta is another constant. And since we are given the initial conditions as C 0 is equal to 0 and C x max is equal to x max, this implies that the compressor characteristic is equal to C x equals x. So, the compressor characteristic is that for a uniform quantizer. Therefore, at high rates, the optimum quantizer is a uniform quantizer. So, if we substitute C x equal to x in the Bennett integral, we obtain an expression for the distortion as and also substituting C x equal to x in the expression for entropy, we obtain the expression for the entropy of this high rate optimum quantizer as follows: H q is equal to H x minus log of 2 x max by L, where H x is the differential entropy. So, this is the differential entropy. Now, it is important to note that this derivation is valid only if the source PDF is bounded by plus minus x max and if the step size is small enough so that we can reasonably assume the PDF to be constant over a quantization interval. So, having studied the different types of quantizer, now let us solve a few more problems related to the design of quantizer. So, let us take problem number 1, which says that consider the signal PDF shown below, assume uniform quantization with the number of levels L equal to 2 raised to nu, where nu is greater than or equal to 3, and the problem is to determine the mean squared quantization error, the variance of the signal and signal to quantization noise ratio in terms of the quantization levels L, and the signal PDF is as shown here. So, the value is between -1 to +1, where it is uniform between -1/4 to 1/4 with the value equal to 1, and other interval it is 1/3. So, let us try to find the solution for this problem. So, let us assume nu equal to 2 plus m, where m is greater than or equal to 1, since we have been given that nu is greater than or equal to 3. Now, if we restrict our design to uniform quantization, then delta j is equal to twice x max by L, which in our case is equal to 2 by L, because x max is equal to 1 and this is equal to 2 by 2 plus m is equal to half times 1 by 2 raised to m. So, for m equal to 1, delta j is equal to 1/4. For m equal to 2, delta j is equal to 1/8, and for m equal to 3, delta j is equal to 1 by 16. Now, because of symmetry of this PDF and the symmetry of our quantizer design, we will restrict our discussion to the interval between 0 and +1. Now, what these results show is that for any m, the interval between 0 to 1/4 is divided into integer number of bands. Let us call that bands as n. and so is the case for the interval between 1/4 to 1. So, this PDF will be divided as follows. Depending on value of m, there will be n number of bands between 0 to 1/4 and the number of bands between 1/4 to 1 will be L by 2 minus n, because L denotes the number of bands between -1 to +1. So, m equal to 1, the number of bands lying between 0 and 1/4 interval would be equal to 1, and the number of bands lying in the interval 1/4 to 1 would be L by 2 minus n is equal to 3. Similarly, for m equal to 2, n would be equal to 2 and this quantity would be equal to 6, m equal to 3, n is equal to 4, and the number of bands in the interval between 1/4 to 1 would be equal to 12. Now, what this result show that PDF is constant over each band and all boundary values and reconstruction levels are also equally spaced. Now, we know that distortion is given by the following expression. Now, in our case, y j is equal to b j plus b j minus 1, that is by 2, that is the mean value of the decision boundaries. Delta j is equal to b j minus b j minus 1, b j minus 1 is equal to y j minus delta j by 2 is equal to y j minus 1 by L, b j is equal to y j minus plus delta j by 2 is equal to y j plus 1 by L. Now, using this values out here and knowing that the quantization design is symmetric, we get this equal to twice L by 2, j is equal to 1 of where squared is equal to and this is equal to which is equal to 2 p y j 3 L cube. Therefore, finally, we can write the expression for the distortion as follows. Which is equal to all the bands in the interval between 0 to 1 by 4 have p y j equal to 1 and all the bands in the interval between 1/4 to 1 have p y j equal to 1/3, and therefore, this reduces to n by 1 plus L by 2 minus n I by 1/3 is equal to 1 by 3 L squared, and the variance for the signal is equal to this can be shown to equal to 0.229, and therefore, signal to quantization noise ratio is equal to 3 L squared by 0.229, which is equal to approximately 0.7 L squared. Now, let us take another example. This example resembles the earlier example which we did for mu law compounding. Now, this is for the A law compounding system, which employs a compressor of this form, and we assume that the input PDF has even symmetry and negligible area outside mod x less than or equal to 1, and we are required to show that the value of the constant K c, which we had discussed in the last class, is given by this, and then for a particular input PDF, that is Laplacian PDF, we are expected to obtain the expression for K c in terms of A and alpha, which is a parameter for Laplacian PDF, and then finally, for specific value of A equal to 100 and L equal to 256, we are required to evaluate the variance of the input, the constant K c, and signal to quantization noise ratio for different values of alphas. So, let us try to provide a solution to this problem. So, the solution would be as follows. For the given A log compounding system, compressor character is given by this. So, the first step is to obtain the derivative for this compressor characteristic in the form of C dash x, which is equal to one plus log A for x lying between 0 and 1 by A, and is equal to 1 plus log A times 1 by x for x lying between 1 by A and 1. Now, we have seen the definition for K c in the last class, that is equal to twice integral from 0 to 1 of the quantity P x divided by C dash x squared dx. Now, if we plug in these values, we get the following expressions. Which can be rewritten as and which is equal to the desired expression. This is equal to S x, that is the input variance, plus twice 0 to 1 by A, 1 by A squared minus x squared P x dx. Now, for the specific case of P x equal to Laplacian PDF, that is alpha by 2 e raised to minus alpha times mod x, it is easy to show that K c is equal to 1 plus log A squared times 1 plus 2 A alpha times A by alpha plus 1 e raised to minus alpha times A. And this is approximately equal to 1 plus log A by A whole term squared if alpha is much larger than A. So, let us try to evaluate the signal to quantization noise ratio, which is given by in dBs is equal to for L is equal to 2 raised to 8, that is 256, and A is equal to 100. Therefore, if we plug in these values in the value for Kc and this expression, then we get the signal to quantization noise ratio as follows, plus 10 log Sx minus 10 log C, and this is shown as follows for different values of alpha. For alpha equal to 16, this is equal to minus 21, minus 6.1, 38.04. For alpha equal to 64, minus 33, minus 17.9, 37.84. And for alpha much larger than A, that is 100, the general expression for signal to quantization noise ratio in terms of input variance is as follows. So, if we plot this, we would get a result something like this. So, what this shows that with the compounding, the signal to quantization noise ratio remains more or less fixed, and this result is similar to what we had obtained earlier for mu law compounding. Now, let us take one more example. Suppose we had the compressor characteristic given by this expression, and it is desired to find the complementary expander characteristic, that is C inverse x, and we are required to evaluate signal to quantization noise ratio when the signal has PDF shown below, it is of this form. So, let us try to find the solution to this. Again, the first step would be to obtain the expander characteristic, that is C inverse x can be shown is equal to x squared for x greater than 0 and minus x squared for x less than 0, which implies that C inverse x is equal to signum x squared for mod x less than or equal to 1. And to calculate the signal to quantization noise ratio, the first step would be to calculate C dash x, which in this case is equal to half mod x minus 3 by 2, and K C can be evaluated as follows. This is equal to twice 4 x cube p x dx, and this can be rewritten for the given PDF as follows. And it can be shown that for this PDF, this expression reduces to 0.672, and finally, signal to quantization noise ratio, which is equal to 3 L squared S x by K C in terms of dB is equal to equals 10 log to the base 10 of 4.46 times L squared times the input source variance is equal to 10 log is 10 4.46 2 raised to 2 m times S x, and less than equal to 6.50 plus 6.02 m, and we will have an upper bound for S x is equal to 1. So, we have studied different quantization schemes for a case where the output of the source is quantized individually. Earlier in our study of lossless compression, we had studied two cases, one where we encode the source output individually, and the second case where we encode the source output in terms of block. We reached to the conclusion that by grouping the source outputs together, we could achieve better compression ratios. So, in the similar manner, we can extend this idea to the case of quantization. Instead of quantizing the individual sample values, we could group the sample values together and quantize them in blocks. We will explore this block quantization in the next class.